All right, let's do some physics. This is a conservation of momentum problem. A 0.23 kilogram bullet moving at 230 meters per second undergoes a completely inelastic collision with a 2 kilogram block of wood that is initially at rest on a level, frictionless surface. Find the speed of the bullet and the block after the collision. All right, so the most important detail about this problem is that the bullet and block undergo a completely inelastic collision. When objects undergo a completely inelastic collision, that means that they're going to stick together and move with the same final velocity. And that detail is critical in order for us to be successful at solving this problem. Realistically, what this means is the bullet probably lodged itself in the block of wood and did not go cleanly through it. So the block of wood was just chilling, the bullet came flying into it, lodged itself into the block of wood, and afterwards the block of wood with the bullet inside of it are probably moving across this frictionless surface. Let's do some math and figure it out. First things first, I defined all of my values. We don't know v1 prime, the velocity of the bullet after the collision, or v2 prime, the velocity of the block after the collision. In order to be successful with this problem, we need to apply the law of conservation of momentum. m1v1 plus m2v2 is equal to m1v1 prime plus m2v2 prime. And we can actually clean this up a little bit. M2 being the block of wood, because the block of wood starts with an initial velocity of 0, this whole second term here can drop out. And because this is a completely inelastic collision, the final velocities have to be the same, meaning v1 prime has to equal v2 prime. So I can actually factor this out. So there's the cleaned up version. We dropped the m2 v2 term, and then we factored out the v prime term. We just need to do a little bit of algebra now to get v prime by itself, and then we can plug in some numbers and solve. So I divided the m1 plus m2 to get v prime by itself, and then I plugged in some numbers and solved for the final velocity. After the collision, the bullet and block are both moving across this level frictionless surface with a velocity of 23.72 meters per second. If you need a minute, this would be a good place in the video to pause. All right, moving on. Part B of this problem says find the amount of kinetic energy lost during the collision. A completely inelastic collision does not conserve kinetic energy, meaning that some kinetic energy actually leaves the system, and we want to just figure out how much. A completely inelastic collision, the most amount of kinetic energy possible is lost, so let's just see how much that is. Change in kinetic energy, or the amount of kinetic energy lost, is going to be Ke prime, the final kinetic energy, minus the initial kinetic energy. And in this problem, the total kinetic energy is always just going to be the kinetic energy of the bullet added to the kinetic energy of the block. First thing you want to do is find the initial kinetic energy. The initial kinetic energy will be the kinetic energy of the bullet plus the kinetic energy of the block, but because the block starts with an initial velocity of 0, we can ignore that term. So the initial kinetic energy is all held by the bullet. Ke is equal to 1/2 mv squared. So using the 0.23 kilograms and the 230 meters per second, we will find that we start with a little over 6,000 joules of kinetic energy. Next thing we want to do is find the final kinetic energy. The final kinetic energy, both the bullet and the block are moving, so we can't get rid of either of these terms. Ke is 1/2 mv squared, so we'll use the mass of the bullet and the mass of the block. And once again, after the collision, the bullet and block are moving with the same velocity. So v prime here is the same number. 1/2 is obviously also the same number. I clean this up a little bit by factoring out a 1/2 v prime squared and just adding the mass of the bullet and the mass of the block. And I plug in some numbers, do the math, and we end up with 627.87 joules of energy. Big energy loss. Started with 6,000 joules and with a little over 600. To figure out exactly how much, I'm going to plug that back in to the delta Ke equation, and we get that negative 5,455.63 joules of energy left our system. The negative sign has to be there because energy is leaving the system, and that's our final answer.